Star.
Let's not draw the Death Star.
Why not? Can you draw the Jabberwocky?
No. Never, never.
I like the springs.
All right, these are springs with different masses hanging off of them. I've got mass 1, I've got mass 2, and what we've said before is that you could define an unstretched length, and I guess we could call this x0, unstretched length, and I guess we would call this x1, and this might be x2, and so this guy would have a delta x value of x1 minus x0. And this guy would have a delta x value of x2 minus x0. We're just talking about the amount that it's been deformed from its regular length, its rest length, its unstretched length. And according to Hooke's law, we say that, and the ideas of elasticity, the spring must be trying to pull upwards on this object, while gravity acts downwards on it. And if the object is sitting there at rest, then the force due to the spring has to be equal but opposite to the force due to gravity. So that the spring force is equal to, or is proportional to, delta x. That's what Hooke said. And it's proportional to delta x such that there's a constant built into it. And what can experimentally be done is we can find k for an object if we know, or if we measure the spring force and divide by the delta x each time. And what you'll find for a nice Hooke's law spring is that the k value will be the same for every stretched force and every stretched length. And we have a few springs that are pretty close to that in the lab. Most of ours are maybe not as ideal as that, but we'd call this an ideal spring. An ideal spring will have the same k value for every fs over delta x ratio that you calculate for that spring. Okay? And we don't have too many really good ideal springs, but we have a few that'll get pretty close in an experiment. This one, the one that's above my head, so over small stretch lengths. If you try to stretch it too much, then it gets to a little bit of a limit where it doesn't act very ideally anymore. You find that with a lot of real springs. So this is really, like everything, we eliminate the realistic. Some of the realistic stuff. When you get out to its extreme stretch length, you get to a point where you're almost turning it into a wire, right? You're uncoiling it almost entirely, and you can imagine when you get it into, well, as you approach it being in wire form, it no longer acts like a spring so much anymore. It really changes some of the properties inside the metal. Yeah.
Is there actually such thing as an ideal spring then?
Well, that's like saying, is there such a thing as, the perfect person? It may be in your mind. And so in our minds, in our minds, you can keep on looking for the perfect person in life, but really the image of the perfect person is only in your imagination and in your hopes and dreams. In our hopes and dreams, springs could work like this, okay? Except in the limit where you turn them into wires, right? Yeah.
Will we ever have to deal with problems on a test where we're not using the ideal spring so that the k value changes?
No, I'm not going to introduce any non-ideal springs. Yeah.
Are you saying none of us are perfect?
Well, perfection, like beauty, is in the eye of the holder for some people, I suppose. Okay, so springs. Back to springs.
This is all on
We have some
video.
deep stuff.
Wow, deep physics stuff. Now the thing is, really and truly, if I want to be good about this, I have to introduce a negative sign because if I want to be honest, the spring force is going to act against the applied force that I give to it, or it's going to work against the displacement. Okay, so the spring force and the delta x are going to be at odds with each other. So some people like to include this negative sign here. Really, for the most part, if you're drawing free body diagrams, you can really just deal with the magnitude of the spring force, and you don't worry too much about that negative sign. But if we're being totally honest about it, there should be a negative sign there.